There are questions in mathematics so simple a 7-year-old can understand them, and so hard that no one on earth can answer them. Pick a number, any number. If it is even, cut it in half. If it is odd, triple it and add 1. Keep going. Does every number eventually fall to 1? Nobody knows. There is a $1 million prize for anyone who can explain why the prime numbers fall where they fall. It has waited a quarter of a century. Unclaimed, 7 problems were given that prize. Exactly 1 has ever been solved, and the man who solved it refused the money and quietly walked away. Tonight, we visit every single one, the famous ones, the forgotten ones, the ones you could draw on a napkin. Slowly, gently, 1 problem at a time. You do not need to solve anything tonight. You do not even need to stay awake. This is every unsolved problem in mathematics, animated, for sleep. And falling asleep here is not a failure. It is the design. The problems will keep unfolding gently, one after another, and wherever you drift off, the rest will simply be waiting for you tomorrow night. Mathematics is very good at waiting, so settle in, let your shoulders sink a little deeper into the bed. Let's begin Chapter 1. Imagine a lecture hall in Paris. It is August of the year 1900. Outside, the city is holding a great World's Fair with pavilions along the river and new electric lamps that turn the evenings gold. Inside this room, it is quieter. Mathematicians have traveled from many countries to be here for the International Congress of Mathematicians, the great gathering of their field, and a man from Germany named David Hilbert rises to speak. Hilbert is not yet 40. He is already one of the most admired mathematicians alive, and the room expects him to announce a discovery, some new theorem of his own. Instead, he does something quieter and much stranger. He stands before the finest minds of his generation and talks about what nobody knows. He has prepared a list of problems, 23 of them. Open questions gathered from every corner of mathematics, chosen because he believes the future of the whole subject runs through them. There is not enough time to present the entire list aloud, so he speaks about only some of it, and the rest is printed and translated and passed from hand to hand and carried home in suitcases to universities all over the world. He offers these questions to the new century the way you might hand someone a lantern at the start of a long walk before dawn. It works better than he could have dreamed. That single lecture sets the agenda for 100 years of mathematics. Whole careers are spent inside those 23 problems. New fields grow up around them the way towns grow up around wells. Some of the problems fall within a few decades. Some hold out for most of the century. And a few are still open tonight, at this very moment, as you lie here listening. Hilbert himself believed, calmly and completely, that no question stays dark forever. We must know, he liked to say. We will know. Those words were later carved on his gravestone, and there is something tender in that. A man resting forever beneath the most hopeful sentence in mathematics. Before we begin our walk, it is worth being gentle and clear about one small word: unsolved. What does it really mean for a problem in mathematics to be unsolved? It does not mean that nobody has an opinion. For most of these questions, nearly every expert alive believes they already know what the answer will turn out to be. And it does not mean that nobody has checked. Computers have tested some of these statements in millions of cases, in billions, sometimes in trillions, and the pattern has held every single time. But in mathematics, checking is not knowing. You can confirm a claim for every number up to 1,000,000, and it can still fail at 1,000,001. You can confirm it out to numbers so large they have no everyday name, and it can still fail somewhere past your last test, out in the endless country you never reached. This has genuinely happened. There are patterns in the history of mathematics that held for stretches of numbers beyond all imagining, and then, quietly, somewhere out past anything a person would ever count to, they broke. So, mathematics asks for something stronger than evidence. It asks for a proof. A proof is a chain of reasoning, link by link, in which every step follows from the ones before it, and no one, however clever, however determined, can find a gap. When a proof exists, the question closes forever, not settled for now, not settled beyond reasonable doubt, closed completely for everyone, for all time. That is the strange and beautiful standard this subject holds itself to, and nothing less will do. And so, until that chain of reasoning exists, even a statement that has passed every test ever run remains officially an open question. It stays on the list. It simply waits. There is something restful in that if you sit with it a while. Mathematics is one of the few places in human life where the words we do not know yet are said plainly without embarrassment, and where waiting 100 years for an answer is considered perfectly ordinary. Nobody rushes. The questions are patient, and the people who love them learn patience too. A century after Hilbert's lecture, in the year 2000, the story came around again. The Clay Mathematics Institute, a foundation devoted to mathematics, announced a new list for a new century. 7 problems this time, chosen as the deepest and hardest questions the subject could offer. They were named the Millennium Prize Problems, and attached to each one was a prize of $1 million. Not because money is what moves mathematicians. It almost never is. The prize was a way of saying to the whole world, in a language everyone understands, these 7 questions matter this much. 7 problems. $1 million each. And in the quarter century since that announcement, exactly one of the 7 has been solved. 1. And here is a small grace note, which we will save for later in the night. The man who solved that one problem was offered his $1 million, and he said no. He turned the prize down and walked away. Why he did that is a story all its own, and it is waiting for you a few hours from now, deep in the middle of this night, if you are still awake when we reach it. And if you are not, it will keep. So that is the shape of tonight, a slow walking tour past every open door in mathematics. We will pause at each doorway, look in for a while at the dark and lovely room beyond, and then move on to the next. Some of these doors have stood open for 160 years, some for centuries. Nobody knows what is on the other side of any of them, and that is not a failure. That is the honest edge of human knowledge, and it is a peaceful place to stand. You do not need to remember any of this. There is no test at the end, and there is nothing you are asked to solve before morning. If your eyes are getting heavy already, that is completely fine. These problems have waited for decades, some for lifetimes, and they are very good at waiting. Every one of them will still be here, still open, still patient when you wake. For now, the lecture in Paris is over. The mathematicians file out into the warm August evening, talking softly, carrying 23 questions home with them. The lamps come on along the river, and the century, with all its unfinished business, quietly begins chapter 2. Begin with something small and familiar. 2, 3, 5, 7, 11, 13. The prime numbers. A prime is a whole number that cannot be broken into smaller pieces by multiplication. It refuses to be divided, and every other whole number is built by multiplying primes together, the way everything material around you is built from atoms. 12 is 2 times 2 times 3. 35 is 5 times 7. The primes are the atoms of arithmetic, and all the rest of the numbers are made of them. More than 2,000 years ago, in the Greek city of Alexandria, Euclid proved that the primes never end. However far you walk out along the number line, there is always another prime somewhere ahead of you. That much is settled, and it has stayed settled for more than 2,000 years. It is one of the oldest proofs we have, and it still holds the way an old stone bridge still holds. But here is the thing about the primes. They keep no schedule. They arrive when they arrive. Sometimes 2 of them come almost together, only 2 steps apart. Sometimes there are long, empty stretches with no prime at all. If you read the primes aloud, one after another, they sound random, like rain falling on a roof. And yet they cannot truly be random, because nothing about them is left to chance. Every prime is exactly where it must be and could never have been anywhere else. The mystery is that we cannot see the rule, and yet, seen from far enough away, the primes behave. As a young man, Carl Friedrich Gauss passed idle minutes counting primes in tables, thousands of them, and he noticed that they thin out in a smooth and gradual way, gentle as dusk coming on. Up close, disorder. From a distance, order. That double nature is the heart of the problem we are visiting first tonight. In the 1700s, Leonhard Euler found the first great bridge into this mystery. He showed that all the primes together are secretly woven into one single mathematical object, a function now called the zeta function. On one face, the zeta function is an endless sum built out of all the counting numbers, every number contributing one small term. On the other face, Euler showed the very same function can be written as a product built out of the primes alone. One object, 2 faces, every number on one side, every prime on the other. Whatever the zeta function knows, it knows about the primes. Then came Bernhard Riemann. The year is 1859. Riemann is a quiet, shy man, gentle in his manners, and one of the deepest mathematical minds who has ever lived. That year, he publishes a paper about the primes. It is the only paper he ever writes on the subject, and it is 8 pages long. 8 pages, and those 8 pages are still, 160 years later, shaping the daily work of mathematicians all over the world. In that paper, Riemann takes Euler's zeta function and carries it somewhere new. He extends it beyond the ordinary numbers it was built for, out over the complex plane, a wide flat plane of numbers spreading away in every direction. And over that plane, the function becomes something you can almost see. A landscape, a dark, rolling surface with rises and hollows spreading to every horizon. In this landscape, there are special places, points where the surface comes down to perfect stillness, to zero. Mathematicians call them the zeros of the function, and they matter because each one carries information about the primes, the way each note in a chord carries part of the sound. And Riemann noticed something about them. The zeros he could find were not scattered across the plane. They lined up. Every important zero he computed stood on one single straight line running through the landscape, the line at 1/2. Mathematicians now call it the critical line, and in the middle of those 8 pages, almost in passing, Riemann set down one quiet sentence. He wrote that it is very likely that all of the important zeros lie on that line. Every single one, forever. He admitted plainly that he could not prove it, and after a few brief attempts, he set the question aside and moved on. That one modest sentence is the Riemann hypothesis, and it has become the most famous unsolved problem in all of mathematics. Ever since, people have gone out into that landscape looking for zeros, first by hand, a few dozen at a time, with pencils and long winter evenings, then with machines. Alan Turing, one of the fathers of modern computing, set one of the earliest electronic computers hunting for zeros, and some accounts say he half hoped to catch one straying off the line. He did not. Every zero he found stood exactly where Riemann said it would. Today, trillions of zeros have been computed. Trillions. And every single one of them sits exactly on the critical line. Not near it. Not almost. Exactly on the line at 1/2 every time. And still, that proves nothing. You may remember why from the start of our walk, checking is not knowing. Beyond the last zero anyone has ever computed, there are infinitely many more, and the hypothesis stands or falls on all of them together. After trillions of confirmations, the question is exactly as open as it was in 1859. Why does it matter so much? Because of what it would say about the primes. Mathematicians have lovely formulas descended from the young Gauss and his tables that estimate how many primes there are up to any given point. The formulas are good, but never perfect. There is always a small error, a soft gap between the estimate and the truth. If the Riemann hypothesis is true, that error stays forever small. It never swells, never runs away, no matter how far out you go. The primes would have a deep hidden order, holding all the way to infinity. All that rain on the roof randomness would be perfectly balanced forever, and we would finally know that the atoms of arithmetic fall as evenly as they possibly can. This problem stands on both of the great lists. In 1900, it was folded into the 8th of Hilbert's 23 problems, and 100 years later it was chosen again as one of the 7 Millennium Prize problems. It is the only question honored on both lists. $1 million waits for whoever settles it, though whoever does will surely not have done it for the money. David Hilbert felt the pull of this problem more than any other. He reportedly said that if he were to fall asleep and wake after 500 years, his very first question would be, has the Riemann hypothesis been proven? Think about that as you drift. 500 years of sleep, whole ages rising and passing like weather. And the first thing he would want to know, before anything about nations or machines is whether those still points truly keep to their line. You are only being asked to sleep until morning, and you do not need an answer even then. If sleep is coming for you now, let it come. The zeros will hold their positions without your help. As far as anyone can tell, they have held them since before there was anyone to look, and if you like, carry one image with you on the way down. A dark landscape rolling gently away in every direction, farther than you can see. Here and there in the darkness, a point of perfect stillness like a small lamp. And every lamp, every single one, standing on the same straight avenue, one straight road running through an endless country. Trillions of lamps, one road, and no one on earth knows why. The landscape does not move tonight. The line holds, as it has always held, and the question rests where Riemann left it, quietly, waiting for a mind that has not yet arrived. Perhaps that mind is asleep somewhere at this very hour, the way you are almost asleep now. Chapter 3. Picture a table by a window, late on a winter evening. On the table there is a jigsaw puzzle, 1,000 pieces. The picture is a harbor at morning, with small boats and gulls and a pale gold sky. A family has been working on it for a week. Every evening, a little more sky came together. Every evening, a little more sea. Tonight, it is finished. And here is the quiet, strange thing at the heart of what comes next. Finishing that puzzle took a week of patient evenings. But if you walked past the table right now, you would know in a single glance that it is done. Every piece in its place, the picture whole. No gaps, no forced corners, no piece pressed in where it does not belong. Checking took you 1 second. Solving took 7 days. Hold on to that feeling. That ordinary, familiar gap between doing and checking is the seed of one of the deepest open questions in all of mathematics. It goes by a name that sounds almost too small for it. P versus NP. Let us take it slowly. Think of a Sudoku puzzle in the back of a newspaper. A 9x9 grid, mostly empty, waiting. Solving it can take a long and wandering while. You pencil in a number, follow the consequences, run into a contradiction, erase, breathe, and try again. A whole evening can disappear into it pleasantly. But now imagine someone hands you a grid that is already filled in and asks a much simpler question. Is this correct? That you can do quickly. You scan each row and make sure nothing repeats. You scan each column. You scan each little box. A few calm minutes and you know for certain. Solving is slow. Checking is fast. Computer scientists noticed that this pattern appears everywhere, and they gave the two sides of it names. P is the family of questions that a computer can answer quickly. Alphabetizing a list of names, finding the shortest route between two towns on a map, multiplying two enormous numbers together. For questions like these, there are clever methods, and the methods stay fast even as the problems grow very large. P is the land of the genuinely easy. NP is a different family and a gentler idea than its name suggests. NP is the family of questions where a proposed answer can be checked quickly. You might have no idea how to find the answer yourself. The search might, as far as anyone knows, take lifetimes. But if someone hands you a candidate, you can verify it without much trouble. The finished jigsaw, the filled-in Sudoku, a seating plan for a wedding where no two feuding relatives share a table, a delivery route that visits every town on the list and still comes home before dark. Hard to find, easy to admire. Every question in P also belongs to NP, because anything you can solve quickly, you can certainly check quickly. The mystery runs in the other direction. Are the two families secretly one and the same? Is every question whose answer is easy to check also, through some cleverness nobody has discovered yet, easy to solve? Wherever recognizing a solution is fast, must finding one be fast as well? That is the entire question. P versus NP. A question you can ask in a single breath, and it has stood open for more than 50 years. For a long time the question floated in the air of the field, felt but never quite stated. Then, in 1971, Stephen Cook made it precise. He gave exact meaning to the words quick and check, so that the question stopped being a mood and became mathematics, a definite statement that must be either true or false. And he found one particular problem, a question about logical formulas that carries within itself the full difficulty of the entire family. The following year, in 1972, Richard Karp did something that changed how everyone saw the landscape. He gathered 21 famous problems that had been troubling people for decades. Problems about scheduling, problems about routing, problems about coloring maps, packing boxes, and splitting groups fairly. On the surface, they looked entirely unrelated, the way a harbor puzzle and a mountain puzzle look unrelated. Karp showed that underneath their costumes, they are all the same problem in disguise. Each one can be translated into any of the others. Crack a single one of them, find a truly fast method for just one, and every one of them falls at the same moment. Problems with this property came to be called NP complete. They are the hardest questions in NP, and they stand together, holding hands in the dark. Thousands more have joined them since. That is what gives this question its strange weight. It is not about one stubborn puzzle. It is about all of them at once. Now, suppose the surprising answer were the true one. Suppose P equals NP, and everything easy to check is secretly easy to solve. The world would tilt in odd ways. Much of the privacy of the internet rests on problems built to be hard in exactly this fashion. Codes that are easy to lock and, as far as anyone knows, slow to pick. If P equals NP, that ground would rest on sand, and something stranger still would follow, something almost philosophical. Checking a mathematical proof, line by line, is fast in this technical sense. So if P equals NP, then finding a proof would be no harder than checking one. The long search a mathematician makes, years of wandering toward one true idea, could, in principle, be replaced by something quick. The distance between searching and recognizing, between creating and appreciating, would quietly collapse. Composing the melody would be no harder than humming it back. Most mathematicians do not believe we live in that world. They believe P does not equal NP. They believe the gap is real, that some questions truly are harder to answer than to check, and that the effort we feel is not an illusion waiting for a trick. 50 years of brilliant people trying and failing to find shortcuts is itself a kind of quiet evidence. But believing is not proving, and here is the delicate heart of the matter. To prove that P does not equal NP, you must show that no fast method exists. Not that we have not found one, that none can exist, by any approach, by any trick, by any idea not yet dreamed of, in any century still to come. Proving that something can be done takes one good idea, one lucky morning. Proving that something can never be done means building a fence around every possible idea at once, including the ones no human mind has touched yet. Nobody knows how to build that fence. The few grand strategies people have tried have each been shown, gently and rigorously, to be unable to finish the job on their own. The question is one of the 7 Millennium Prize problems, and a prize of $1 million waits for whoever settles it in either direction. The prize has waited since the year 2000, and it is in no hurry at all. Neither are you. If your eyes are growing heavy, it is fine to let them close now. The question will keep perfectly well until morning, as it has kept for half a century, because in the end, P versus NP is the mathematics of effort itself. It asks whether the work was necessary, whether the week of evenings spent at the table was the only honest road to the finished harbor, or whether some impossible shortcut lay hidden in the box all along. Everything we feel about trying, that searching is harder than finding, that building is harder than admiring, is folded inside this one unproven sentence. The puzzle rests on the table by the window. The house has gone quiet. The question of why it was hard remains open, softly, like a door left ajar for the night. Chapter 4. Now let the puzzle pieces rest where they are, and think about water. In the 1800s, 2 men, working in different countries and in different decades, wrote down the laws of flowing things. The first was Claude Louis Navier, a French engineer who spent his working life among bridges and roads, a practical man surrounded by stone and iron. In the 1820s, he asked what the laws of motion would say about a substance with no fixed shape at all, water, air, anything that pours, and he wrote down equations for it. Some years later, George Gabriel Stokes, a mathematician born in Ireland who spent his long career at Cambridge, arrived at the same equations along his own path and set them on firmer ground. The two never worked together, yet their names are joined now, and will stay joined for as long as the subject is studied. The Navier-Stokes equations, the equations of flowing water and moving air. What the equations say is, at heart, quite simple. They are the old laws of motion, the ones that govern falling apples and orbiting moons, rewritten for a fluid. Follow one small parcel of water. It is pushed by the pressure of its neighbors. It is dragged and slowed by friction as it slides past them, strongly in honey, lightly in water, hardly at all in air, and it is carried along by the very current it belongs to. A rider on a river made of riders. Write all of those influences down carefully, at every point, at every moment, and you have Navier-Stokes. We trust these equations with our lives, every single day. Tonight's weather forecast exists because computers spent the afternoon solving Navier-Stokes across the whole sky, ocean to ocean. The wings of every airplane in the air right now were shaped by these equations, tested against them. Long before any metal was cut, they describe the blood that your heart is quietly moving through you at this very moment, along wide vessels and narrow ones. And they describe small, unimportant, lovely things too, the swirl of cream in a cup of evening coffee, folding into spirals and slowly fading. The equations know that swirl, and yet, here is what nobody on Earth knows. Take a fluid in 3 dimensions, real, ordinary space, the kind water actually lives in. Start it off perfectly smooth and calm, no sharp edges in the motion, no violence anywhere, every current gentle and orderly, like a pond a moment after you stop stirring it. Now let the equations carry it forward in time, on their own, with no one touching anything. The question is this: must the flow stay smooth forever? Or can the fluid, following the equations faithfully, gather its own motion inward, concentrating it into a smaller and smaller region, spinning faster and faster, until at some definite, finite moment the mathematics breaks and the equations predict an infinite speed at a single point? Smoothness forever, or a breakdown in finite time? That is the millennium question for the Navier-Stokes equations. With $1 million set aside for whoever answers it, the equations themselves are about 200 years old. The question is open. Nobody knows. It is worth pausing on how odd that is. This is not a question about some exotic object at the far edge of mathematics. It is a question about water, about whether the equations we use for rivers and wings and weather are, in the deepest sense, whole, or whether they carry, folded inside them, the possibility of their own undoing. Part of what makes it hard is the way fluids share their energy. A big, lazy swirl feeds smaller swirls, and those feed smaller ones still. Energy cascading down from eddy to eddy, like water down a terraced hillside. You have watched this in the smoke above a candle, smooth at first, then folding, then a fine, soft chaos of curls. The question is whether that cascade always spreads the motion out and calms it, or whether the equations permit it, just once, in just the wrong arrangement, to focus everything onto a single point instead. In 2014, Terence Tao, one of the most celebrated mathematicians alive, found a clue about how deep the difficulty runs. He studied not the true equations, but an averaged, simplified cousin of them, a version that keeps much of their structure while being easier to steer. And he showed that this cousin really can break down. He arranged its flow to behave almost like a machine built out of water, gathering its energy, passing it inward to smaller and smaller scales, each stage quicker than the last, until, in finite time, it surged past every bound. This does not settle the real question. The true equations have extra structure that the cousin lacks, and that structure may be exactly what keeps real water safe. But it is a hint, offered honestly. It hints that the true equations may hide something wild within them, and it means that any future proof of eternal calm will have to be very clever indeed, clever enough to see precisely what separates the true equations from the cousin that fails. So the question rests exactly where honesty leaves it. Perhaps smooth flows stay smooth forever, and someone, someday, will show us why. Perhaps somewhere in the mathematics, there is a way for water to focus itself toward a point of infinite speed, something never seen in any ocean or any kettle, living only in the equation's deep interior. Either way, no one has yet reached the bottom of it. Say it gently and let it be. Nobody knows, and there is a strange comfort in that. Humanity flies on these equations. It sails on them, forecasts tomorrow's rain with them, designs harbors and heart valves with them. We ride a river whose depths have never been fully measured, and the river carries us anyway, day after day, faithfully. The equations have never needed our complete understanding in order to hold us up. You do not need to hold any of this in mind. If sleep is drifting in, let it come. The water will go on flowing whether or not anyone is watching it. Picture, last of all, a glass of water on a bedside table in a dark and quiet room. Hours ago it was poured, and it swirled and trembled and caught the light. Now it is still. Every current inside it has faded, each eddy handing its last motion down to smaller and smaller ones, until there was nothing left to hand down. The surface is flat and calm. Somewhere far away, rivers are running and oceans are turning under the night. But here, in the dark, the water has found its level, and it rests, and so can you. Chapter 5. Come forward now to 1954. On Long Island, in New York, there is a physics laboratory set among pine trees, a quiet campus of low buildings where people think about the insides of atoms. In one of its offices, two physicists share a desk and a blackboard. One is Chen-Ning Yang, a young professor visiting for the year, already known for the quickness of his mind. The other is Robert Mills, younger still, a graduate student finishing his doctorate. They talk. They fill the blackboard, erase it, and fill it again. And before the year is out, they write down a set of equations together. They are not trying to win a prize. They are following a hunch about symmetry, the old physicist's faith that the deepest laws of nature should stay the same no matter how you turn them. Their equations describe a field, something like the electromagnetic field that carries light and radio through the air around you now, but stranger and richer. In an ordinary field like light, the messengers of the force are neutral. One beam of light passes through another beam of light without ever noticing it. But in the field Yang and Mills imagined, the messengers of the force carry charge themselves. The field tangles with itself. Its ripples pull on its own ripples. It is a field that feels its own weight. At first, almost nobody knew what the equations were for. They sat quietly for years, admired by a few, used by almost no one. And then, slowly, through the 1960s and 70s, physicists realized what they had been handed. These equations are the grammar of the strong nuclear force, the force that glues every atomic nucleus together. Deep inside every atom, particles called quarks are bound into protons and neutrons are bound into nuclei, and the binding, all of it, follows the equations from that shared office on Long Island. Every atom in your body, every atom in your pillow, in the walls of your room, in the slow night air, held at the center by Yang and Mills. And the equations work. That is the astonishing part. Physicists feed them into enormous computer simulations, some of the largest calculations human beings have ever run, and the answers that come out match experiments beautifully. The masses of particles, computed from nothing but the theory itself, land where the measurements say they should. By every practical test, this is one of the most successful descriptions of nature ever written down. So here is the strange and gentle secret. No one has ever proved that the theory truly exists. Not in the physical sense. The force is real. The nuclei hold. In the mathematical sense, when a mathematician asks, precisely, what object are you talking about? What is this quantum field? Defined rigorously, with every step justified from first principles, no one can quite answer. Physicists calculate with the theory the way you might drive a beloved old car whose hood you cannot open. It runs. It has always run. It has never once failed you on the road. But no one has ever really seen the engine. The Millennium Problem asks for two things. First, show that the quantum theory, built on the Yang and Mills equations, exists as honest, rigorous mathematics, not only as a recipe that happens to work. And second, show that the theory has what is called a mass gap. The mass gap is the beautiful part, and there is a picture you can rest inside. Think of a drum. An ordinary drum skin can be touched so lightly that it barely sounds at all. Tap it more and more softly, and the sound fades smoothly towards silence, quieter and quieter, with no lower limit. Most fields in physics are like that. The electromagnetic field is like that. A wave of light or radio can be as gentle as you please, carrying almost no energy at all, whispering all the way down to nothing. But the field of the strong force seems to be a different kind of drum, a drum skin that refuses to whisper. Every note it can make, even the very quietest one, costs at least a certain minimum amount of energy. There is no sound softer than its softest note. Below that threshold, there is no faint murmur, no half-heard hum. There is only true silence. That minimum price is the mass gap. It is why the strong force reaches only across the tiny width of a nucleus and no further. It is part of why matter is crisp and solid, why the world keeps its shape while you sleep. Everything measured says the gap is there. Every experiment agrees. Every simulation agrees. Physicists do not doubt it, not really. And still, no one can prove it from first principles. Not yet. The $1 million attached to this problem is, in effect, a reward for making physics honest. For taking a theory the whole world already trusts, a theory holding every atom together at this very moment and building the floor beneath it. I want to be honest with you about how abstract all of this is. You are not expected to picture a quantum field tonight. No one can, not really, not even the people who work with these equations every day of their lives. They hold the idea loosely, the way you hold a word from a language you are still learning. Mathematicians hold it loosely too, so you are allowed to hold it loosely as well. And if the whole idea slips out of your hands as you drift, that is exactly as it should be. Keep only the drum if you keep anything at all. A deep, patient drum that will not whisper, resting at the heart of every atom. Somewhere in you, right now, the strong force is doing its quiet work, holding every nucleus without being asked, the way it has since before there were oceans. The proof can wait another century if it needs to. The holding does not wait. Everything is held together tonight, whether or not anyone can yet say why. Chapter 6. Of the 7 Millennium Problems, 2 are almost never spoken of outside mathematics itself. No one makes films about them. They appear in no headlines. Even people who love science, people who could tell you about black holes and prime numbers, will often draw a gentle blank at their names. They are the quiet ones of the family. So let us give them the softest telling of the night, which is, after all, how quiet things prefer to be told. The first belongs to William Hodge, a Scottish mathematician who spent most of his life at Cambridge, thinking slowly and deeply about shape. In 1950, at a great gathering of mathematicians, he stood up and described a pattern he believed in, but could not prove. It has carried his name ever since. Here is the landscape he was walking in. Take an equation, the ordinary kind, with letters raised to powers, x squared and y cubed and sums of such things. Now gather up every point that satisfies the equation, and look at what you have gathered. You have a shape. A simple equation carves out a circle or a sweeping curve. Richer equations, with more letters, carve surfaces like rolling landscapes made of pure logic, and beyond those come forms with more dimensions than the eye can hold. Shapes no one can see, though mathematicians learn to walk around inside them anyway, feeling their way like people moving through a familiar house at night. These shapes can have holes. A ring has one hole. A pretzel has 3. The shapes carved by equations can have holes too. And in higher dimensions, they can have kinds of holes that have no everyday names. Hollows and handles and tunnels of a completely abstract sort. Hodge looked at these holes and asked a question that sounds almost innocent. Can the holes themselves be described by equations? His conjecture says, roughly, yes, that certain kinds of holes, in shapes carved from polynomial equations, can always themselves be traced out by equations of the same kind. The hole is not merely an absence, a place where the shape happens not to be. It has an algebraic identity of its own. If Hodge is right, then geometry and algebra agree with each other at the very deepest level. 2 languages describing one world with nothing lost in translation. I will be honest with you. The words certain kinds are carrying a great deal of quiet weight in that sentence, and stating the conjecture precisely takes years of preparation. Most mathematicians hold the full statement loosely, like a shape seen through frosted glass. You are welcome to hold it even more loosely than that. A shape, its holes, and the hope that every hole has a name. That is plenty. The second quiet problem begins in Cambridge too, in the early 1960s, in a room that hums. 2 mathematicians, Brian Birch and Peter Swinnerton Dyer, are working with a machine called EDSAC, one of the very first computers, a room-filling creature of wires and glowing valves. They are using it to count. What they are counting are solutions on elliptic curves. An elliptic curve, despite its name, is not an ellipse. It is the shape drawn by a certain kind of equation, one with an x cubed inside it, and it makes a smooth, graceful curve that arcs and loops across the page. Mathematicians have loved these curves for centuries because they sit at a perfect depth, simple enough to write in a single line, deep enough that no one has ever touched the bottom. The question Birch and Swinnerton Dyer asked is old and simple. Which fractions solve the equation? Some elliptic curves have only a handful of these rational solutions, a few points scattered along the curve. Others have infinitely many, an endless ladder of fractions climbing forever. Telling the 2 kinds apart just by looking at the equation is remarkably hard, so they set their machine counting curve after curve, night after night, and they watched the printouts for a pattern. And a pattern came. Out of those columns of numbers rose one of the strangest suspicions in modern mathematics. To each elliptic curve, you can attach a single function called an L function built from the curve's own arithmetic. Their conjecture says that if you look at this function at one single special point, its behavior there tells you how rich the curve's rational solutions are, whether the supply is finite or infinite, written in the way one function touches one point, a whole infinity of arithmetic folded into a single spot. Pieces of this have since been proved beautiful pieces in special cases. The whole of it remains open. If that feels abstract, it is because it is, honestly and completely. Even the people who work on it describe it with a kind of respectful squint. You are not meant to see it clearly tonight. No one does. But here is the reason to feel hopeful about these two quiet problems, and it comes from the elliptic curves themselves. In 1637, a French lawyer and mathematician named Pierre de Fermat wrote a note in the margin of a book. He claimed that no three positive whole numbers can make a power plus a like power equal a third like power. Once the power climbs past 2, he added that he had a marvelous proof and that the margin was too small to contain it. Then he closed the book. That claim waited 357 years. Generations of mathematicians grew up with it, worked their whole lives on it, and passed it on unsolved. And then Andrew Wiles, who had first read about the problem in a library book when he was 10 years old, worked on it in near secrecy for 7 years, in an attic study, telling almost no one. When he finally announced a proof, a subtle gap was found, and for a difficult year, the whole thing wavered. Then, with the help of a former student named Richard Taylor, he mended it, and in 1994, the proof stood complete. 3.5 centuries of waiting, and then, within one lifetime, the door simply opened, and the bridge Wiles crossed was built out of elliptic curves, the very objects Birch and Swinnerton Dyer had fed to their patient machine 30 years before. So the quiet problems are not forgotten problems. They are seeds in slow soil. Somewhere, perhaps, a child has already borrowed the library book that begins the story of their solving. If sleep has been circling you through all of this, let it land now. Nothing here needs an answer tonight. The shapes keep their holes, the curves keep their secrets, and both keep them gladly, having done so for a long time, in no hurry at all, like the night itself. Chapter 7. Near the beginning of tonight, I made you a promise. I told you that one of these great problems has actually fallen, that it was solved quietly in our own lifetime by a man who then turned down every reward the world tried to press into his hands. This is that story, and of all the stories in modern mathematics, it may be the most peaceful one. It begins in 1904 with Henri Poincaré. Poincaré was French, born in the city of Nancy, and he was one of the last people who seemed able to hold all of mathematics inside a single mind. He studied the orbits of planets. He studied the physics of light and time. He wrote about how discovery itself feels, the way an answer can surface while you are stepping onto a bus, thinking of nothing at all. And along the way, almost as a side effect of everything else he was doing, he helped invent a new science, the science of shapes that stretch. Today we call it topology. In ordinary geometry, a circle and an oval are different things. In topology, they are the same thing, because you can stretch one into the other without cutting and without tearing. A topologist does not measure distances or angles. A topologist asks softer, deeper questions. What is connected to what? Where are the holes? What survives when a shape is allowed to bend like warm clay? Here is the picture to hold, and you can hold it loosely. Imagine the surface of a ball, a sphere. Now lay a loop of string anywhere on that surface. You can slide the loop around. You can tighten it little by little, and no matter where it began, it will always shrink down to a single point. There is nothing on a sphere for the string to catch on. Now imagine the surface of a donut. Lay a loop of string on it, and most of the time the same thing happens. The loop slides, shrinks, and vanishes to a point. But there is one kind of loop that cannot do this. A loop that passes through the hole of the donut is caught. The hole holds it. You can slide that loop forever, and it will never come free. So the sphere has a special gift. Every loop on it can be shrunk away to nothing. And in 1904, Poincaré asked a question that sounds almost innocent. Move up one dimension to the three-dimensional sphere. This is a shape we cannot quite picture. It curves through a fourth dimension the way the surface of a ball curves through our third, and it closes back on itself, finite and whole, with no edge anywhere. Poincaré asked, "Is the three-dimensional sphere the only closed three-dimensional shape on which every loop shrinks to a point? Or is there some other shape out there, an impostor, sharing the gift without being the sphere?" He suspected the sphere stands alone. He could not prove it, and for 100 years, neither could anyone else. Brilliant mathematicians announced proofs. Some of the announcements survived for months before a flaw was found. Some survived only days. Careers were devoted to it. Whole new tools were invented for it. Tools that went on to solve other problems, while this one stayed closed. It became, gently and by common agreement, the most famous question in topology. In the year 2000, the Clay Mathematics Institute named it one of 7 Millennium Prize problems and set the same bounty on each of them, $1 million. Then came the idea that changed everything. In 1982, an American mathematician named Richard Hamilton proposed something beautiful. Imagine a bar of metal, hot in some places, cool in others. Leave it alone, and the heat spreads. Warmth flows into the cold spots. Sharp differences soften, and in time, the whole bar settles to one even temperature. Hamilton imagined doing the same thing to a shape itself. Let curvature flow the way heat flows. Let the lumpy places relax and the crumpled places unfold, so that the shape smooths itself slowly toward its own true form. He called this the Ricci flow, and the hope was this: if every closed shape on which all loops shrink must flow, in the end, into a perfect round sphere, then the sphere really is the only one. And Poincaré was right. Hamilton carried this program a long, long way. But there were places where the flow broke down. A shape could pinch into a thin neck, like taffy pulled too far, and at the pinch, the mathematics stopped making sense. For years, no one knew how to carry those moments. Then, in November of 2002, With no fanfare at all, a paper appeared on the open internet. No journal, no announcement, not even Poincaré's name in the title. Its author was Grigory Perelman, a quiet mathematician from St. Petersburg in Russia. 2 more papers followed in 2003, posted the same way, free for anyone in the world to read. Together, in dense and modest language, they did what a century of effort had not done. They tamed the pinches. They carried Hamilton's flow past every breakdown. They completed the program, and resting at the bottom of it all, almost like a postscript, was the answer to Poincaré's question. Yes, the sphere stands alone. There is no imposter. The experts did not believe it at once, and they were right to be careful. Claims about this problem had come and gone for 100 years, so teams of mathematicians around the world sat down with Perelman's papers and began to check, line by line, filling in every compressed step. It took years, and it held. Every gap could be closed. Every argument was sound. After a century, the question was answered, and then came the strangest, sweetest part of the story. In 2006, Perelman was offered the Fields Medal, the highest honor in mathematics. He declined it. In 2010, the Clay Institute offered him the $1 million Millennium Prize. He declined that too. He said that Richard Hamilton, whose flow he had completed, deserved as much credit as he did. He said he was not interested in money or fame. And then he stepped away from mathematics altogether and went home, and he lives quietly in St. Petersburg to this day. People sometimes tell this story as a mystery or as something sad. I do not think it is either. Here was a man who wanted one thing. The answer. He worked mostly alone for 7 years until he had it. Then he gave it away freely to the whole world at once and asked for nothing back and closed the door softly behind him. There is a completeness in that. A problem asked, a problem answered, and a person at peace with both. If sleep is close now, you can let it come. This is a story you can leave at any point because it ends well from every direction. Of the 7 millennium problems, this is still the only one ever solved. A question asked in 1904, 100 years of trying. An answer freely given, and somewhere in St. Petersburg tonight, the man who found it is sleeping too. Chapter 8. At the very beginning of tonight, we played a small game with numbers. You may remember it, or it may have drifted away by now, and either way is fine. The rules fit inside a single breath. Pick any counting number. If it is even, cut it in half. If it is odd, triple it and add 1. Look at what you have and do it again. Take 6. 6 is even, so it becomes 3. 3 is odd, so triple it and add 1, and you have 10. 10 is even, so 5. 5 is odd, 16 is even, so 8. Then 4. Then 2. Then 1. And once you reach 1, the game folds into a tiny loop. 1 becomes 4, 4 becomes 2, 2 becomes 1, around and around, like a wheel spinning slower and slower. 1 is where the game comes to rest. This little game entered mathematics in 1937 in the notebooks of a German mathematician named Lothar Kolatz, who liked to play with rules that shuffle numbers around and watch where they lead. The conjecture that carries his name says something very simple. Every starting number, every single one, eventually falls to 1. No number climbs upward forever. No number circles in some strange loop of its own, out beyond where anyone has looked. All of them, the conjecture says, come home to one. Mathematicians often call it the 3n+1 problem, because that is the entire recipe. There are famous problems that take years of study before you can even understand what is being asked. This one you can explain to a child at breakfast, and the child can start checking numbers with a crayon before the toast is gone. That is part of its charm. It is also part of its mystery, because nothing this easy to say, you would think, could stay hidden for this long. The numbers this game produces are called hailstone numbers, and it is a lovely name. Inside a storm cloud, a hailstone does not simply fall. The wind carries it upward. It gathers a thin coat of ice. It drops, it is caught again, and it rises again, over and over, until at last it grows heavy enough to land. The numbers behave the same way. Halving pulls them down. Tripling lifts them up. They tumble and soar, and then, every time anyone has ever watched, they land. Some of them take remarkable journeys. Take 27. It looks harmless, sitting there below 30. But 27 climbs and crashes and climbs again, riding updrafts you would never expect, soaring as high as 9,232 before it finally loses its lift. It takes 111 steps to land at 1, and the number standing right next to it, 28, glides down in a small fraction of that. Neighbors can have completely different flights. No one can look at a number and easily say how long its storm will last. And yet, as far as anyone has ever seen, every storm ends. Computers have looked very far indeed. Every starting number up to roughly 2 to the power of 68 has been checked. That is a number 21 digits long. Every single one of them falls to 1. Not one exception, ever, anywhere. And here is the humbling part, and it deserves to be said gently. All of that proves nothing. There are infinitely many counting numbers, and however far a computer climbs, infinity remains exactly as far away as when it started. Mathematics asks for certainty about all numbers at once, and no list of examples, however long and however clean, can ever supply it. Somewhere past everything checked, the numbers keep their own counsel, and if the conjecture were ever to fail, a number would have to do one of only two things. It would have to climb forever, drifting upward without end, or it would have to settle into some distant loop of its own, circling far away from 1. In all the searching across all those 21 digits, no one has ever glimpsed either. Why is something so simple so hard? Partly because the two rules pull against each other in a tangled way. Halving is calm and predictable. Tripling and adding 1 stirs everything up, changing evens into odds and odds into evens with no easy pattern. The game keeps braiding multiplication and addition together, and mathematics has surprisingly few tools for braids like that. Paul Erdős thought so too. Erdős was a wandering Hungarian mathematician who spent his life traveling from problem to problem the way other people travel from city to city, living out of a suitcase, asking after open questions the way one asks after old friends. He looked at this little game and gave a famous verdict. Mathematics, he said, is not yet ripe for such questions. And he offered $500 of his own money to anyone who could prove it. The money has never been claimed. The closest anyone has come arrived in 2019. Terence Dow, an Australian mathematician widely regarded as one of the finest problem solvers alive, proved that almost all starting numbers eventually sink almost all the way down. Almost all the way. Those careful, doubled words are the honest edge of human knowledge. It is a deep and beautiful result, and Dow himself was clear about its limits. It does not say that every number reaches 1. No one alive can say that yet, and there is a quiet hint that this game may be hard for a reason. John Horton Conway, a playful English mathematician who loved games of every kind, studied cousin versions of the rule, games built the same way but with slightly different steps. He showed that some of those cousins are formally undecidable. No procedure, no computer, no method of any kind can settle what they do. The original game is not known to be like that, but it comes from a family with real depths, and that is worth a moment of respect. So this is where the simplest unsolved problem in the world rests tonight. A rule a child can play with a pencil, a conjecture tested beyond 2 to the power of 68 without a single exception, a $500 prize still waiting, and no proof anywhere on earth that the falling always happens. You do not need to keep count anymore. If your eyes are heavy, let them close, and the numbers will finish falling without you. Picture them, if you like, as stones on a long hillside above a stream. Each one tumbles in its own way. Some skitter straight down to the water. Some, like 27, take the long path, rolling up over ridges, pausing on ledges, before gravity gathers them again. But the slope only leans one way, and the water below is patient. One by one, as far as anyone has ever watched, every stone comes down to the stream and settles at 1. The stream moves softly over them all, and the numbers sleep. Chapter 9. Picture a coastline at night. The water is calm, the sky is dark and moonless, and along the shore, at strange and irregular intervals, lighthouses are shining. Each one is a prime number: 2, 3, 5, 7, 11, 13. The numbers that cannot be divided into anything smaller, the numbers that are only ever themselves. You are walking this coastline, slowly, with no particular hurry. Near the beginning, the lights come often. You can stand beneath one lighthouse and see the next one glowing just down the shore. But as you walk on, something changes. The lights begin to thin. The stretches of dark sand between them grow longer. This is not chance. It is a law of the numbers themselves. The further you travel, the rarer the primes become. There are places, far out along this coast, where you can walk for what feels like miles without passing a single light. And yet, every so often, you see something that makes you pause. 2 lighthouses standing almost side by side, 2 primes separated by just 2 steps, 11 and 13, 17 and 19, 29 and 31. Mathematicians call them twin primes, pairs of lights keeping each other company in the dark. Here is the gentle mystery at the heart of this part of the night. The primes keep thinning out forever, so you might expect the twins to fade away entirely. At some point, surely, the growing gaps should win, and one last pair of lights should stand alone at the edge of everything. But that is not what we see. However far anyone has ever looked and people have looked very far indeed. The twins keep appearing. Rarer, yes, farther and farther between, but never seeming to end. Do they truly go on forever? That question is called the twin prime conjecture. Nearly every mathematician believes the answer is yes, and yet no one has ever proved it. It is a question you can explain to a child in one quiet minute, and it has drifted through centuries of brilliant minds, unhurried and unanswered. There is a companion mystery, just as simple and just as patient. In the year 1742, a mathematician named Christian Goldbach wrote a letter to his friend Leonhard Euler, one of the greatest mathematicians who has ever lived. In that letter, Goldbach shared a guess. Take any even number bigger than 2, he said, and it seems you can always write it as 2 primes added together. 4 is 2 plus 2. 10 is 3 plus 7. 100 is 3 plus 97. Every even number, Goldbach suspected, is built from exactly 2 of those lighthouse numbers. Wrote back that he believed it completely. But he could not prove it. Neither could Goldbach. And in all the years since, neither has anyone else. Computers have checked, of course. They have tested every even number up to 4 times 10 to the power of 18. That is a 4 followed by 18 zeros. Every single even number in that vast range splits neatly into 2 primes, without one exception. But checking is not proving. There are infinitely many even numbers, and no computer, however patient, can visit them all. Somewhere past the horizon of everything we have tested, the pattern could, in principle, break. Almost no one believes it will. But believing is not the same as knowing, and mathematics waits for knowing. One softer version of the puzzle has been settled. If you ask about odd numbers instead, and allow 3 primes rather than 2, the answer is finally known. Every odd number beyond a small starting point is the sum of 3 primes. That result, called the weak Goldbach conjecture, was fully proved in 2013 by a mathematician named Harold Helfgott. It was a true summit reached, a genuine piece of the mountain brought down. The main peak still stands untouched. If your eyes are growing heavy while the primes drift past, that is quite all right. Let them close. The lighthouses will keep shining, whether we watch them or not. In 1912, a German mathematician named Edmund Landau stood before a gathering of his colleagues and listed 4 problems about prime numbers. He called them unattackable in the science of his day. The first was Goldbach's guess. The second was the twin primes. The third asked whether there is always at least 1 prime waiting between one perfect square and the next. The fourth asked whether infinitely many primes have the form n squared plus 1, sitting just 1 step above a perfect square. More than a century has passed since Landau spoke. All 4 problems remain open. Not one has fallen, but the story of the twins does have a recent turning, and it is one of the most moving stories in modern mathematics. It belongs to a man named Yitong Zhang. Zhang earned his doctorate in mathematics, and then, for years, almost nothing went the way it was supposed to. He could not find an academic position. He worked wherever he could. For a time, he worked at a Subway sandwich shop. For a time, he kept the books at a motel. And through all of it, quietly, alone, with no colleagues and no title, and no reason for anyone to expect anything of him at all. He kept thinking about prime numbers. Eventually, he found work as a lecturer, teaching calculus to undergraduates, still almost entirely unknown. By 2013, he was 58 years old, an age at which people often say mathematicians have long since done their best work. That year, Zhang submitted a paper, and in it, he proved something that no one in history had ever managed. He could not show that infinitely many primes differ by exactly 2, but he showed that infinitely many pairs of primes differ by at most 70 million. 70 million sounds enormous, and it is. But hold on to what it means. Out along that endless coastline, where the gaps between lights grow without limit, there are always, forever, pairs of lighthouses within 70 million steps of each other. The pairs never run out. For the first time in the history of the subject, the distance between prime pairs had a ceiling. A finite number stood where, for thousands of years, there had been nothing at all. Mathematicians around the world read the paper in something like wonder. And then they went to work together. A young mathematician named James Maynard found powerful new methods of his own. A large open collaboration on the internet, called Polymath, invited anyone who wished to help, and many did, sharpening the argument in public, line by line, for all to see. Together, in a matter of months, they drove Zhang's 70 million down and down. Today, the bound stands at 246. Infinitely many pairs of primes differ by at most 246. And there the number has rested year after year ever since. To push it all the way down to 2, to reach the twins themselves, will take ideas that no one on Earth has had yet. So the twins keep their secret a little longer. Somewhere impossibly far along the coast, 2 lights stand close together above the still water, and past them, we believe, 2 more, and past those, 2 more again, without end. No one can promise yet that this is true, but tonight it is enough to walk the shore and see the paired lights in the distance and trust the quiet pattern that has never once failed us. The sea is calm. The lights are steady. You can rest here as long as you like. Chapter 10. Let the coastline fade now and drift further back in time, more than 2,000 years, to the warm stone courtyards of ancient Greece. The mathematicians there treated numbers almost as living things. They gave them characters and virtues. And, among all the numbers, they searched for the ones that seemed, in some quiet way, complete. Consider 6. The numbers that divide into it evenly, apart from itself, are 1, 2, and 3. Now add them together. 1 plus 2 plus 3 is 6. The number is built exactly and entirely from its own parts, nothing missing, nothing left over. The Greeks called such a number perfect. They went looking for more. The next perfect number is 28. Its divisors are 1, 2, 4, 7, and 14. Add them slowly. 1 plus 2 plus 4 plus 7 plus 14. And you arrive at 28 again. The same gentle balance, holding a second time. After that, perfection becomes rare. The third perfect number is 496. The fourth is 8,128. And there the ancient world stopped. In all their centuries of searching, the Greeks found only those 4. 4 perfect numbers in the whole known universe of counting. Euclid, The great geometer, whose textbook would be read for 2,000 years, noticed something hidden inside these numbers. Each one is connected to a special kind of prime, a prime that is exactly one less than a power of 2. 3 is one less than 4. 7 is one less than 8. 31 is one less than 32. And Euclid found a recipe. Whenever you have such a prime, multiply it by half of its power of 2, and a perfect number appears. 7 times 4 is 28. 31 times 16 is 496. The recipe never fails. It is among the oldest theorems in all of mathematics, and it still works tonight, exactly as it worked in the ancient world so long ago. The special primes in that recipe have a name. In the 17th century, in Paris, there lived a monk named Mersenne. His small monastery cell became one of the crossroads of European thought, not because of what he discovered there, but because of the letters that passed through it. Mersenne wrote to nearly every mathematician and scientist of his age, and they wrote back, and through him, they spoke to one another across the whole continent. In a world without journals, he was the network itself. He studied those primes that sit one below a power of 2, and they carry his name to this day. Mersenne primes, and here the ancient story flows straight into our own time. The largest known prime numbers in the world right now are Mersenne primes. They were not found by governments or famous laboratories. They were found by ordinary people, volunteers, whose home computers quietly test enormous numbers through the night as part of a project called the Great Internet Mersenne Prime Search. Somewhere, at this very hour, machines are humming in dark and sleeping houses, sifting numbers with millions of digits, looking for the next one. And each new Mersenne prime, through Euclid's old recipe, gives the world a new perfect number. Anyone can join this search. You simply let your computer take part, and it works while you rest. And if it ever happens to find the next great prime, your name becomes part of a story that began in ancient Greece. Yet after 2,300 years, the two deepest questions about perfect numbers remain exactly where the Greeks left them. The ancients wondered about them. Euclid could not settle them. Euler could not settle them. Neither, so far, can we. Are there infinitely many perfect numbers? No one knows. Every new Mersenne prime gives us one more, but no one can prove that the supply will never run dry. And the second question is, stranger and lovelier still, every perfect number ever found is even. Leonhard Euler, the same Euler who received Goldbach's letter, proved that every even perfect number must come from Euclid's recipe, but nothing we know forbids an odd one. Does an odd perfect number exist? None has ever been found. Computers have searched deep into the numbers, and we now know that if an odd perfect number exists at all, it is larger than 10 to the power of 1,500. That is a 1 followed by 1,500 zeros. It may be out there, somewhere, vast beyond all picturing. It may not exist at all. Mathematics, honest as always, simply says, we do not yet know. There is nothing here you need to remember, by the way. If sleep is gathering at the edges of things, let it come. These questions have waited longer than empires. They will certainly wait through the night. One more pair of numbers deserves to be spoken before this part of the night ends. 220, and 284. Add up everything that divides 220 apart from itself, and the total is 284. Add up everything that divides 284 apart from itself, and the total is 220. Each number is made from the parts of the other. Mathematicians call them an amicable pair, friendly numbers. And there is an old story, a legend carried down the centuries, that the followers of Pythagoras treasured this pair as a symbol of true friendship, two souls, each composed of the other. One version of the tale says that when Pythagoras was asked what a friend is, he answered, "Another self," the way 220 and 284 are to each other. We cannot be certain the story is true, but it has been told for a very long time, and it is a gentle thing to hold as you drift. This is the oldest unfinished business in mathematics. Questions asked before most nations on earth existed, before the languages we speak tonight were ever spoken. Perfect numbers, friendly numbers, waiting with perfect patience. They do not mind the waiting. They have watched empires rise and settle back into dust, and they have simply gone on being what they are. The numbers were here long before us, and they are not going anywhere. Somewhere a home computer is quietly searching. Somewhere the next perfect number is resting, undiscovered, in the dark. The questions will keep. Let the night hold them for you now. Chapter 11. There is a kind of mathematics you can hold in your hands. It needs no towers of abstraction, no heavy machinery, no strange new numbers. It needs a pencil, a sheet of paper, and a little patience. Tonight, in this quiet stretch of the night, we walk slowly through a small gallery of such problems. 5 little drawings, each one simple enough to show a child, each one still open after all these years. You do not need to solve anything here. You only need to look the way you would look at pictures in a dim museum after closing time, and let each one settle before moving to the next. Begin with a loop. In 1911, a German mathematician named Otto Toeplitz asked a question so simple it feels like a puzzle for children. Draw a closed loop on paper, any closed loop at all. It can be round like a pond, or wobbly like a coastline, or scribbled like a signature, as long as the line wanders back to where it began. Toeplitz asked whether somewhere on that loop there must always be 4 points that form a perfect square, not roughly a square, a perfect one with all 4 corners resting exactly on your curve. Tilted is allowed, tiny is allowed, but perfect. For smooth loops, the gently curving kind with no sharp corners and no wild behavior, the answer is yes, and mathematicians have proved it. For wilder loops, the truly jagged ones, the infinitely crinkled ones, no one knows. More than a century of pencils and doodles, and the inscribed square problem is still open. Every closed curve you have ever drawn on every envelope and every napkin may be quietly holding a perfect square inside it. Probably it is. We simply cannot yet say so for certain, and there is something restful about that. A secret the scribbles keep. Now imagine a sheet of paper with no edges. It goes on forever in every direction, flat and endless and blank. Your task is to give every single point of it a color. There is only one rule. If 2 points are exactly 1 unit apart, 1 small fixed step, they must not share a color. How many colors do you need? This question is called the chromatic number of the plane, and it is often known as the Hadwiger-Nelson problem, after Hugo Hadwiger and Edward Nelson, two of the people who thought about it in the middle of the 20th century. Here is what makes it remarkable. For 70 years, the state of knowledge did not move at all. The answer was known to be 4, 5, 6, or 7. Nothing sharper than that. Generations of mathematicians came and went, whole careers began and ended, and those 4 possibilities stayed exactly where they were. Then, in 2018, something lovely happened. Aubrey de Grey, a biologist known for his research on aging, a man who did mathematics simply for the joy of it, in his spare hours, found a clever arrangement of points that cannot be colored with only 4 colors. At least 5 are needed. An amateur working for love moved a frontier that had not moved in a lifetime. It is a gentle reminder that these problems belong to everyone. The full answer, 5, 6, or 7, is still out there, waiting somewhere on that endless sheet. The third drawing comes with a love story. It is the 1930s. In Budapest, a circle of young mathematicians meets in parks and cafes to trade problems the way other friends trade gossip. One of them, Esther Klein, brings a puzzle about points scattered on a page. Scatter enough points, she notices, and some of them must always form a convex shape, a shape with no dents in it, the way a triangle has no dents. How many points does it take to guarantee this? Among the friends who take up her puzzle are George Sakaris and Paul Erdos. Klein and Sakaris begin working on the question together, and somewhere between the points and the proofs, they fall in love. They marry, and that is why Erdos, with his dry warmth, called it the happy ending problem, and the name has stayed ever since. The general question is still open. How many scattered points are enough to force a convex shape with n corners? The conjectured answer is beautifully tidy, 2 to the power of n minus 2 plus 1. Mathematicians believe it. Progress has come remarkably close in recent years, but the last step has not been taken, and so the problem named for a happy ending is still waiting patiently for its own. The fourth drawing moves. Picture a circular running track at night, lit softly, with no crowd in the stands. A handful of runners set off from the same starting line, each at their own constant speed, no 2 speeds alike, and they run forever, around and around, never tiring, never stopping. The lonely runner conjecture says this: every runner, at some moment, finds themselves far away from all the others, with a comfortable stretch of empty track on every side. Every runner is eventually lonely. Not sad, just alone for a while, with room to breathe. The conjecture has been proved when the number of runners is small. For larger groups, it remains open, which is a strange and gentle thought that we cannot yet promise every runner their moment of solitude, though we believe it always comes. If your eyes are growing heavy, you can let them close now. The runners will keep circling without you, lap after lap, each of them drifting, sooner or later, into a quiet stretch of track all their own. One last drawing before we rest. Take a sphere, like an orange, and ask how many identical oranges can touch it at the same time, all pressed snugly against its surface. In our familiar 3 dimensions, the answer is 12, and even that took centuries of argument to settle. mathematicians ask the same question in higher dimensions, spaces we cannot picture but can describe with perfect precision. These counts are called kissing numbers, a friendly name for a hard question. And here is the honest truth. They are known in only a scattering of dimensions. In most dimensions, nobody knows. Rows and rows of simple questions about touching spheres, unanswered, like a shelf of round, unopened jars. But let this little gallery end on hope, because problems you can almost draw really do fall, sometimes. In 2016, a Ukrainian mathematician named Marina Vyazovska solved the sphere packing problem in dimension 8, finding the densest possible way to arrange spheres there, with a proof so clean and surprising that other mathematicians described it the way you might describe music. With collaborators, she then settled dimension 24 as well. In 2022, she received the Fields Medal, one of the highest honors mathematics can give, a question people could almost sketch on paper, open for generations, answered at last by a single beautiful idea. The other drawings in this gallery are still waiting for theirs. One day, perhaps, each will meet its idea, and someone not yet born will see what we could not. For tonight, they rest on the page, simple and patient, like sketches left on a desk in a dark and quiet room. Chapter 12. We end this stretch of the night with the softest question of all. It is the one puzzle you are formally allowed to stop working on, not because anyone gave up, but because mathematics itself, in a way we will come to slowly, has said that no one is required to answer it. It concerns infinity, and it begins with counting. In the late 19th century, a mathematician named Georg Cantor did something that sounds impossible. He measured infinity. Before him, infinity was a single vague vastness, a word for whatever has no end. Cantor looked closer and found structure. He found that some infinities are genuinely larger than others. Take the counting numbers. 1, 2, 3, and onward forever. They make an infinity, the most familiar one, the infinity of things you could list if you had endless time. It is the infinity of an endless staircase, each step following the last. Now take a line, smooth and unbroken, and consider every point on it. That is the continuum, the seamless flow of positions with no gaps at all. Cantor proved that this second infinity is strictly larger than the first. However cleverly you try to write the points of a line into a list, 1 point per row of your endless notebook, some point always escapes. Not because your list is badly made, but because no list can ever be long enough. There are more points on a line than there are counting numbers. 2 infinities, one truly bigger than the other. It is one of the strangest and most beautiful facts a human being has ever proved. And then Cantor asked a natural question. Between those 2 sizes of infinity, is there a third? Something strictly larger than the counting numbers, yet strictly smaller than the continuum? And in between infinity, a mezzanine floor between the ground and the first landing? Cantor believed the answer was no. He believed the 2 infinities sit directly beside each other with nothing in the gap. That belief is called the continuum hypothesis. He spent years trying to prove it. He never could. The question outlived him, and it grew in stature. In 1900, David Hilbert, then perhaps the most influential mathematician in the world, stood before a great congress in Paris and read out a list of the problems he hoped the new century would solve. The continuum hypothesis was first on the list. Of all the open questions in all of mathematics, this was the one he placed at the very top. What happened next is one of the quietest, most remarkable stories in the history of thought. It came in two halves, a generation apart. The first half came from Kurt Gödel around 1940. Gödel showed that if you start from the standard axioms of mathematics, the accepted ground rules on which ordinary mathematics is built, you can never disprove the continuum hypothesis. You can add it to the rules, assume it is true, and no contradiction will ever appear. The hypothesis fits. Whatever else the axioms can do, they cannot refute it. The second half came in 1963 from a young mathematician named Paul Cohen. Cohen invented a new technique and showed the mirror image. From those same axioms, you can never prove the continuum hypothesis either. You can assume it is false, and again, no contradiction will ever appear. For this work, Cohen received the Fields Medal. He had shown mathematics a door it did not know it had. Now place the two halves side by side, gently, like closing a book. The standard rules of mathematics can neither prove the hypothesis nor disprove it. The question is what mathematicians call independent. It is not that the answer is hidden, waiting on some unread page. It is that the rules we have all agreed to reason from simply do not decide it. Every other problem in tonight's journey is a locked door that we believe has a key. This one is different. This one turned out to be not unanswered, but unanswerable, at least from where we stand. So what is true? Here is the calm, honest picture. There are two coherent mathematical worlds. In one of them, the continuum hypothesis holds, and there is no infinity between the counting numbers and the line. In the other, it fails, and an in-between infinity exists. Both worlds are internally consistent. Both obey every axiom we have accepted. Nothing in our rules chooses between them. Mathematicians can walk into either world and do perfectly good mathematics there, and many have. Picture it, if you like, as a corridor at the end of a long house, late at night. Two doors, side by side. Behind one door is a room where the hypothesis is true. Behind the other, a room where it is false. You open the first door. The room is quiet, well made, and nothing in it is broken. You close it softly and open the second. This room is quiet too, well made too, and nothing in it is broken either. You stand in the corridor between them, and you understand, slowly, that the house itself has no preference. No draft pushes you toward one door or the other. No floorboard creaks a warning. Both rooms belong. Both rooms are allowed. Some mathematicians believe the story is not quite over. They wonder whether there is a deeper, truer axiom still waiting to be found, some principle so natural that, once seen, everyone would accept it, and it would finally settle the question one way or the other. Others doubt that any such axiom will ever command agreement. That conversation continues, unhurried, in seminar rooms and journals, and it may continue for a very long time. It is honest to say that no one knows, but notice what all of this means for you here tonight. Every other puzzle in this long night asks, somewhere underneath, for effort. Someone someday is supposed to solve it. This one asks for nothing. The work was done, And the answer was that the question rests outside the reach of our rules. You are holding a puzzle that mathematics itself has set down. So you may set it down too. If sleep is close now, let it come and carry you. Drifting off in the middle of the continuum hypothesis is not giving up. It is, in a way, the correct response. Two infinities, one small and one large, and between them, a question our rules will not answer. Somewhere, Cantor's counting numbers go on and on, one after another, and the points of the line flow past them, uncountably many, smooth as water in the dark. The two quiet rooms stand side by side, doors ajar, both consistent, both calm. No one has to choose tonight. The corridor is still. The house is at rest. And so, slowly, are you. Chapter 13. Somewhere in Kyoto, there is a proof that may or may not be a proof. It is roughly 500 pages long. Only a handful of people on Earth have read it all the way through, and they do not agree on what it says. To understand how mathematics arrived at such a strange, quiet impasse, you have to begin with a question so simple. It fits in a single breath: addition and multiplication. You learned them side by side as a child, and they feel like siblings. But deep down, they are nearly strangers. Multiplication is about how a number is built, which primes it is made of, stacked and repeated like bricks in a wall. Addition does not care about any of that. It simply pushes two quantities together, and when it does, their inner architecture is shuffled beyond recognition. The building plans are lost. In 1985, David Masser and Joseph Oesterle gave this old tension a precise shape. Their idea became known as the ABC conjecture, named for the three numbers in the simplest equation there is: A plus B equals C. Roughly, it says this: if A and B are numbers of a very particular kind, numbers built from many repeated prime factors, the same small primes multiplied over and over, then their sum, C, is almost never a number of that kind as well. Multiplicative richness does not survive addition. There are exceptions, but the conjecture says they are rare, and that beyond any chosen level of extravagance, there are only finitely many of them, ever, in all the endless numbers. It sounds modest. It is not. If the ABC conjecture is true, whole families of famous results, theorems that took decades, entire careers, hundreds of pages, would follow from it in a few lines, the way 100 locked doors might all answer to a single master key. Number theorists have wanted that key for a long time. Then, in August of 2012, something remarkable happened. Shinichi Mochizuki, a mathematician at Kyoto University, quietly posted 4 papers on his webpage. Together they ran to roughly 500 pages, and in them he claimed a proof of the ABC conjecture. But the papers were not written in the ordinary language of number theory. Over many years, working largely alone, Mochizuki had built an entirely new mathematical world of his own, which he called inter-universal Teichmuller theory. New objects, new definitions, new ways of saying what a number even is. To read the proof, you first had to learn the world. Almost nobody could. The papers sat there, vast and self-contained, like a sealed library whose catalog is written in a language of one. A small circle of mathematicians close to Mochizuki studied the work for years and said it was sound. Most others, including some of the finest number theorists alive, walked slowly around the outside of the building, and could not find the door. If your eyes are drifting closed somewhere among those 500 pages, by the way, let them close. This story does not need you to keep watch. It has rested unresolved for years, and it will still be resting, gently in the morning. In March of 2018, two deeply respected mathematicians, Peter Scholz and Jakob Stix, traveled to Kyoto to try to settle things in person. For a week they sat with Mochizuki and worked through the heart of the argument, face to face. They left unconvinced. In their view, one key step, deep inside the proof, a single load-bearing inference, had not been justified. Mochizuki's view was, and remains, exactly the opposite. He maintains that the proof is complete, and that his critics have misunderstood the theory they are judging. Each side found the weak clarifying. Each side came away more certain than before. In 2021, the papers were formally published in a mathematical journal. A journal, it should gently be said, where Mochizuki himself is editor-in-chief, though the journal stated he stepped aside from the decision. Publication usually ends these stories. This time, it did not. Most number theorists around the world still do not accept the proof. A smaller group maintains that it is correct and always has been. Both camps are made of serious, careful people, and so the ABC conjecture rests tonight in a twilight almost unique in mathematics. A claimed proof exists in print, and the community cannot agree on whether it is one. Perhaps a bridge will someday be built between the two shores. Perhaps a different, simpler proof will arrive and let everyone rest. For now, nobody knows, and it is all right not to know. And here is the gentle twist in tonight's story. A proof can go unread because it is too new, written in a language only one person speaks. But a proof can also go unread because it is too large for any human at all. In 2016, Marine Huel and his colleagues settled an old question about Pythagorean triples, sets of three whole numbers where the first squared plus the second squared equals the third squared, like 3, 4, and 5. The question was about color. If you paint every whole number either red or blue, must some triple somewhere end up all one color? Or is there a clever coloring that avoids it forever? A computer found the answer. You can color the numbers up to 7,824 and dodge every single colored triple. Add one more number and it becomes impossible. Every coloring, without exception, fails. The proof of this fact was generated by machine, and it was 200 terabytes in size. At the time, it was the largest proof ever created. It is true. It has been checked by other programs down to the last logical step, and no human being has read it or ever will. It is a path no one can walk, leading to a place we now know is real. Paul Erdős, the wandering Hungarian mathematician who published more papers than any other mathematician in history, liked to talk about the book. God, he said, smiling, because he was never sure he believed in God, keeps a book containing the most beautiful proof of every theorem, the perfect argument for each truth, the one you read and simply say a yes, of course. When Erdős met a proof he loved, he gave it his highest compliment. This one, he would say, is from the book. Some of its pages we have found, short, luminous arguments that feel less invented than discovered, like the ancient proof by Euclid of Alexandria that the primes never end, and some of its pages are still blank. So what is a proof for, if not to be understood? Tonight there is a proof one man says is finished, and the world cannot read, and a proof the world trusts that no single mind can hold, and an imagined book of proofs so clear they hardly need reading at all. Maybe understanding is the point. Maybe certainty is. You do not have to decide. The question can rest on the nightstand like a book laid face down, keeping its own place until morning. Chapter 14. One last wondering before the night ends. Why do the hardest problems wait so long? What, exactly, are they waiting for? It is not money. In Texas, there is a banker named Andrew Beale who taught himself number theory and loves it the way other people love music. Years ago, exploring equations about powers, he noticed something. Take two perfect powers, numbers raised to exponents bigger than 2. In every example he could find where two such powers added up to a third, the three base numbers always shared a common factor. He came to believe this must always happen. And then he did something very natural for a banker. He put up a prize, $1 million, for a proof or a disproof, the money held safely in trust by a mathematical society, ready for the day someone earns it. That day has not come. The problem does not seem to notice the prize at all. It simply stays open, season after quiet season, as if it had somewhere better to be than solved. And Beale is not alone. Several of the problems you have heard about tonight carry prizes of $1 million as well. The money waits patiently in its accounts. The problems do not hurry for it. Whatever they are waiting for, it has never once been money, because problems do not live on human time. Consider the most famous wait of all. In 1637, a French lawyer named Pierre de Fermat sat reading by candlelight in the south of France. The book in his hands was an old volume of arithmetic, written many centuries earlier by Diophantus of Alexandria, a book of puzzles about whole numbers, already ancient when Fermat opened it. An idea came to him, and he wrote it in the margin, a claim that a certain simple equation about powers has no solutions at all, together with one of the most famous sentences in mathematics, that he had discovered a truly marvelous proof, which the margin was too narrow to contain. Then he turned the page and went on with his evening. He never wrote that proof anywhere. In time, he died, and the note remained. The margin note waited. It waited through revolutions and empires, through the rise and fall of currencies and kingdoms, through the whole slow turning of the centuries. It waited 357 years, and then it met a boy. Andrew Wiles was 10 years old when he wandered into a library in Cambridge, in England, and opened a book that described Fermat's claim. He could understand the question, a child could, and he learned that no one on earth could answer it. He never really put it down. He grew up. He became a mathematician, one of the finest of his generation, and the problem waited for him the way it had waited for everyone. And then, for 7 years, in an attic study at the top of his house, he worked on it in secret, telling almost no one. 7 years of mornings at the same desk, while the world assumed nothing was happening. 7 years of small steps, wrong turns, and quiet returns. There was a stumble near the end, a gap discovered, a long, hard year of repair, And then, in 1994, 357 years after the margin note, it was done. Problems outlive kingdoms. They outlive currencies and languages, and every single person who poses them. Fermat's little sentence outlasted the France he wrote it in, the money he was paid in, the law he practiced, and every human being alive on the day he wrote it. An unsolved problem may be the most patient thing our species has ever made, and now the night is nearly over, and you can let the last of it go. Wherever you are in your drifting, halfway down, or long since gone, that is exactly the right place to be. Listen one last time while the lights go out. All through this long night you have walked past open questions the way you might walk past lit windows in a sleeping town, and every one of them is still glowing softly behind you. The primes are still out there along the dark coastline, keeping their secret, pairs of them glowing close together far into the distance, farther than anyone has proven they must. The numbers are still tumbling, patiently, down toward one, rising, falling, hailstones drifting through arithmetic. Every number anyone has ever tested finding its way home, and no one able to promise that all of them do. The runner is still circling the track among the others, each at their own steady pace, and somewhere in the long night, we believe, each one becomes briefly, gently lonely, far from all the rest at once, for just a moment. Though no one has yet proven it for every runner, the two quiet rooms of the Continuum are still standing side by side, one where the in-between infinity exists, and one where it does not, both consistent, both perfectly furnished, both waiting, with nothing in mathematics forcing us to choose between them. And the landscape of the zeta function still stretches away under the stars, and every one of its still points found so far stands on one straight avenue, a single line, never once broken, as far as anyone has ever looked. Here is the last thing, and then you can sleep. Every unanswered question is a door left open, and an open door is not a threat. It is an invitation, one that never expires, that stays open across the centuries, that anyone may walk through, or simply stand beside, feeling the air move gently from the other side. Somewhere on Earth right now, someone is awake over a notebook, pushing softly at one of these doors. Let them. That work is theirs tonight. Yours was only this, to stand at the open doors for a little while and look through them at everything we do not yet know. You do not need to solve anything. You never did. Wherever you drifted off tonight, an hour ago, a minute ago, or somewhere in the middle of this very sentence, it does not matter, and nothing was lost. Every one of these problems will still be here tomorrow night, unhurried, unchanged, patient as stone. Thank you for spending this night among the unsolved. Sleep deeply and dream slowly. Good night.